Maged2 and the regulation of renal salt transporters. Maged2 encodes melanoma-associated antigen D2 and maps to the X chromosome. We also identified two different Maged2 mutations in two families with idiopathic polyhydramnios. Maged2 affects the expression and function of the sodium chloride cotransport NKCC2 and NCC, K components of saline reabsorptions in the distal renal tubule, possibly through adenylyl cyclase and cyclic MP, signaling an acetoplasmic head shock protein.
Hey everyone, this is Eric again from Stanford University and the Palo Alto VA Hospital. This is the first video in a 5-video series on sodium and potassium disorders, and the topic will be the normal physiology involved in sodium, potassium, and water balance. I personally really enjoyed this topic, but I appreciate this may not be true for everyone. So my goal here is to make this video the last lecture on this topic you'll ever need, by explaining the content as clearly as possible using plenty of diagrams, as well as making it thorough enough to include all of the details you may need to know down the road. The maintenance of a healthy and stable balance in the concentrations of sodium and potassium, along with the appropriate amount of water in our bodies, is a classic example of homeostasis. Control of this particular homeostasis is a highly complicated process involving numerous interconnected physiologic pathways, dozens of enzymes, and over a dozen hormones. Luckily, a complete understanding of all of this is not necessary for the routine practice of medicine. However, a sufficient understanding for medical practice is still quite involved, and if you are coming into this video series already feeling overwhelmed by this topic, don't worry, that's very common. I found that sodium-potassium water homeostasis can be made more accessible by teaching it in layers, starting from a big picture without specifics, then moving to the details of individual pathways, and ending with a return to the big picture, now with the details filled in. This is the learning process I'll be using here. I won't be turning you into the world expert in the physiology, but rather provide you all of the necessary physiology background to allow you to diagnose and treat the vast majority of patients with disorders of sodium and potassium balance. The key players of sodium-potassium water homeostasis that I'll be discussing can be broken down into 3 categories. There are 3 major hormones, 7 minor hormones, and 2 critical enzymes. If it's not listed here, it's not clinically relevant. So let me start now with the big picture without details. This will represent the sodium, potassium, and water that is present in our blood. There are 4 arms or domains of physiologic processes that closely interact to keep these in balance. First is the GI system. We take in these electrolytes and water.
Barrett syndromes is a rare genetically heterogeneous disorder characterized by renal salts wasting, hypokalemic metabolic alkalosis, and secondary hyperaldosteronism, with normal to low blood pressure. Two distinct presentations of syndrome exist: antenatal Bartter syndromes and classic Bartter syndromes. Both forms are inherited as autosomal recessive traits. Patients with antenatal Bartter syndromes may carry loss-of-function mutations in the genes encoding the furosemide-sensitive sodium-potassium chloride cotransporter, the inwardly rectifying potassium channel ROMK submit Bartin. The concerted action of these transporters in the renal thick ascending limb of the loop of Henle ensures transcellular sodium chloride reabsorption.
Bartter syndrome is a rare inherited defect in the thick ascending limb of the loop of Henle. It is characterized by low potassium levels, increased blood pH, and normal to low blood pressure. There are 2 types of Bartter syndrome, neonatal and classic. The closely associated disorder, Guy-Tellman syndrome, is milder than both subtypes of Bartter syndrome. Features: in 90% of cases, neonatal Bartter syndrome is seen between 24 and 30 weeks of gestation with excess amniotic fluid. After birth, the infant is seen to urinate and drink excessively. Life-threatening dehydration may result if the infant does not receive adequate fluids. About 85% of infants dispose of excess amounts of calcium in the urine and kidneys, which may lead to kidney stones. In rare occasions, the infant may progress to renal failure. Patients with classic Bartter syndrome may have symptoms in the first 2 years of life, but they are usually diagnosed at school age or later. Like infants with the neonatal subtype, patients with classic Bartter syndrome also have polyuria, polydipsia, and a tendency to dehydration, but normal or just slightly increased urinary calcium excretion without the tendency to develop kidney stones. These patients also have vomiting and growth retardation. Kidney function is also normal if the disease is treated, but occasionally patients proceed to end-stage renal failure. Bartter's syndrome consists of hypokalemia, alkalosis, normal to low blood pressures, and elevated plasma renin and aldosterone. Numerous causes of this syndrome probably exist. Diagnostic pointers include high urinary potassium and chloride despite low serum values, increased
Pros: the initial presentation was more severe than in known types of antenatal Bartter syndrome, as reflected by an early onset of polyhydramnios and labor. All symptoms disappeared spontaneously during follow-up in the infants. With cons, we identified mutations in the renal salt transporters that were responsible for the loss-of-function mutations in the genes encoding the furosemide-sensitive sodium-potassium chloride cotransporter.
Renin-angiotensin-aldosterone system. The renin-angiotensin-aldosterone system is a classic endocrine system that helps to regulate long-term blood pressure and extracellular volume in the body. The system begins with the release of angiotensinogen into circulation by the liver. This may be in response to low blood pressure and adverse changes in sodium concentrations. An enzyme, renin, is secreted which cleaves angiotensinogen to form the inactive decapeptide angiotensin 1. Further transformation of angiotensin is carried out by angiotensin converting enzyme, or ACE. This is predominantly found in the pulmonary circulation. However, ACE is also produced in the vascular endothelium of many tissues, including the kidney, adrenal gland, brain, and heart. The angiotensin converting enzyme converts the inactive precursor angiotensin 1 into the vasoactive peptide angiotensin 2. In addition, alternative pathways exist that do not rely on either renin or ACE. In non-renin pathways, enzymes like tonin and cathepsin D release angiotensin 1 from angiotensinogen and tissue plasminogen activator, or TPA, and can make angiotensin 2 directly from angiotensinogen. This bypasses the midway production of angiotensin 1. Enzymes like chymase can form angiotensin 2 from angiotensin 1 via an ACE-independent pathway. Angiotensin converting enzyme also degrades bradykinin, which is required for synthesis of a major vasodilator, nitric oxide. Angiotensin 2 binds AT1 receptors expressed on the surface of vascular endothelium and impairs nitric oxide synthesis as well. Reduced bioavailability of nitric oxide combined with the stimulation of AT1 receptors on smooth muscle cells causes vasoconstriction. In addition to a vasoconstriction effect, stimulation of AT1 receptor causes the adrenal glands to release the hormone aldosterone, resulting in sodium retention. Combined with vasoconstriction, this increases blood pressure. In the final stages of RAS, the kidney reduces the production of renin. Most of the known actions of angiotensin II are mediated through the AT1 receptors, which can be found in the kidney, heart, vascular smooth muscle cells, brain, adrenal glands, platelets, adipocytes, and the placenta.
In Ecuador, there is not too much genetic studies, but doctors and scientists state that 3 pregnancies with male offspring in one family were complicated by severe polyhydramnios and prematurity. One fetus died, the other 2 had transient massive salt wasting and polyuria reminiscent of antenatal Bartter syndrome.
All right, greetings everyone. Let's jump into some heavy stuff here. This is going to seem a little overwhelming at the beginning, but you're going to see this quite a bit, and it's really important for you to grasp these concepts early. So if you don't have an anatomy and physiology course or two, or any background in A&P, you'll see that throughout the course you'll just need to kind of refresh yourself and get yourself up to speed. So I'll provide these little videos. There's also a tremendous amount regulation, and certainly there are more electrolytes than just the 3 that are listed. Just these 3 happen to be the most important in my estimation, and they happen to be the most relevant to the pre-hospital setting. We have millions and millions of nephrons, excuse me, and they're all doing this business for us of filtration and reabsorption and secretion. So these are the 3 things that kidneys do. The kidneys, they filter all of the blood for us, essentially. They secrete things, meaning that they can make certain molecules and put them back into our blood. And then, of course, they can reabsorb things so that we can maintain the things that we need, like glucose, for example. Your body needs to get that glucose back into its system. We don't want to just pee glucose out. That wouldn't make any sense. Your body works so hard to get that glucose from whatever it is you ate. You eat a cookie and you get glucose out of it. It's pretty remarkable. So your body's put in a ton of energy. It's got a lot invested in it, and so it's going to be able to selectively decide what things it should keep, what things it needs to get rid of, because they're either toxic or they're in excess quantity in your body.
Conclusion: Maged2 mutations cause X-linked polyhydramnios with prematurity and a severe but transient form of antenatal Bartter syndrome. Maged2 is essential for fetal renal salt reabsorption, amniotic fluid homeostasis, and the maintenance of pregnancy.
I'm Robert Dillman, a medical oncologist and cancer researcher in California. For more than 30 years, I've been involved in the development of cancer biological therapies and immunotherapies, including monoclonal antibodies, lymphocyte therapies, and cancer vaccines. Doug Press asked me to write a review covering melanoma vaccines because of the great interest in this approach. A comprehensive review entitled Melanoma Vaccines, Trials and Tribulations is now available in the online journal Vaccine, Development and Therapy. We know melanoma can respond to immune therapies. 3 immunotherapy products are already approved to treat melanoma, and others are under development and or about to be approved. This review covers many variables associated with melanoma vaccines, including adjuvants and co-stimulatory agents, sources of melanoma-associated antigens, and the results of clinical trials, which are summarized in a series of tables. Many vaccines are given with co-stimulatory agents called adjuvants. The various classical adjuvants that have been used as components of melanoma vaccines are reviewed, as well as clinical trials of melanoma vaccines that have employed cytokines, including alpha and gamma interferon, interleukin-2, and GM-CSF. Recognition of the importance of dendritic cells for antigen presentation has led to a number of trials testing anti-melanoma dendritic cell products using peptides or tumor cells as sources of antigen. There are many possible sources for melanoma-associated antigens, including specific molecules recognized by monoclonal